Hey there, chemists. By now you should be comfortable with looking at chair conformations for six-membered rings and being able to identify if a substituent is either equatorial, like that methyl group right there, or axial right there. What we're going to do today is interconvert those drawings from chair conformation representations to just flat hexagonal representations. So I want you to imagine that you have this molecule in front of you and you're shrunken down and literally hovering above the molecule like so, and then you're going to draw what you see. So we've been drawing chairs as if we're looking at them along their edge, and now I want to draw it as if it's just a hexagonal projection. We should convey most of the same information, just not as much as we see in a chair. So if I do that, let me start by drawing a hexagon template. I'm going to pick one carbon to start. I'll say that this highlighted carbon right there is that spot in my six-membered ring. This is arbitrary, but relative to that, everything else has to be correct. Now, if I think about floating above that chair right there, that methyl is ever so slightly toward me. I know that because it's up and equatorial right here. There is a down and axial hydrogen that's farther away from me. So I'm going to draw that hydrogen in with a bold line, like so. Sorry, that methyl group with a bold line. And then I'm going to work my way around the ring and fill in every other substituent accordingly. So let me skip 2 carbons and get to this methyl. Relative to my perspective, that methyl is away from me. So I'm going to skip 2 carbons in the ring on the left and draw that methyl pointing away from me. And here we have an up methyl that's toward me, a down methyl that's away from me. That's all we're conveying in this, the relative direction of those 2 methyl groups. There's one more methyl, it's also pointing away from me, so I'll show it with a dashed line in the flat hexagon form. And what you should notice is that you don't convey as much information in the hexagonal representation as you do in the chair. We can see relative direction, up versus down, but we can't see axial versus equatorial. Now I want to do one more thing and convert this back into a chair and prove to you that there's more than one way you can represent a correct chair conformation for this one molecule right here. I'm going to draw it actually slanted in the other direction just to switch it up a little bit. I'm going to do the same thing. I'm going to pick this carbon here as an arbitrary starting point, and I will say that that spot is this carbon right here. Again, it's arbitrary where I start. And if that methyl is coming out of the page toward me, I'm going to say that that means it's up. Up at this carbon is axial. So I'm going to draw it up and axially right at that spot. Let's work our way around the ring and get to the other methyl groups. Skip 2. I have a methyl over here that's away from me with a dashed line, so that's down. Skip 2 carbons, I get to here. Down at this carbon is equatorial. So I'm going to show equatorial. Remember, the axial bonds alternate up, down, up, down, up, down around the ring, and they're usually drawn parallel to the edge of your page. The equatorial bonds also alternate down, up, down, up, down, and up, but they're not parallel to the edge of your page. They're actually parallel to other parts of the ring. That's usually the convention. So they still have relative direction to each other. There's one more. There's this methyl here. That would be on this position. That's also down. And at that carbon, it's axial. So look at what we have here compared to what we started with. This is the same compound. I didn't accidentally draw a constitutional isomer or even what we have yet to learn, what's called a stereoisomer. But clearly things have changed. We went from 2 equatorial methyls and an axial methyl to 2 axial methyls and an equatorial methyl. The relative direction up versus down is the same, but axial became equatorial and equatorial became axial. What I drew, actually on purpose here, is what's called a ring flip. Now let me show how this happens. Here is a cyclohexane molecule, and unlike what we draw, they're not static. They actually can pucker and twist, and you can rotate around single carbon-carbon bonds. Whenever you do that, you get what's called a conformational isomer. And for every single 6-membered ring, there are 2 possible chair conformers that we can interconvert between. Here's one in front of you. This is just regular cyclohexane. And I want you to focus on the hydrogen all the way to the right. All the way to the right, I see a hydrogen. They drew this green plane right through the middle of it, just to designate what's above and below. We'll call it up and down. Right now, that hydrogen all the way to the right is up and equatorial. Let's see what happens when it undergoes a ring flip. So the bonds are twisting. It's contorting differently. We're not breaking bonds. It's just twisting out of the plane a little bit and back in. And then we have a new chair. Now, if you were following that same hydrogen, it was up and equatorial. Now it's up and axial. So when a ring flip happens, everything that's axial becomes equatorial, and everything that's equatorial becomes axial, which means both are possible. Why does this matter? Well, some reactions will only occur if a certain substituent on a ring is in one of those positions. In fact, not too long, we'll learn about a type of reaction where a certain type of atom has to be in an axial position in order for it to undergo that reaction. So as chemists, we can control this by building things into the molecular architecture to force that group to be in an axial position in its most stable conformation. Let's let this ring flip back to the original one. If you're following the same hydrogen, it was up and axial, and then it goes back to up and equatorial. And these are interconverting back and forth. That's what a ring flip is called. So let me make a note of that right now since we just saw it. In a ring flip, axial becomes equatorial, and equatorial becomes axial. That's key. And both chairs are possible. You'll also notice from that animation, there's other conformers that exist, aren't there? There's not just the two chairs. Some chemists give names to these things. There's what's called a twist chair. There's a twist boat. I didn't actually see a boat in that animation, but they exist as well. For this class, we're just going to focus on the two chair conformers because those are the most stable of the possibilities. And today we'll see we can come up with arguments of how one of those is probably more stable than the other. So let's practice this. Here's a different cyclohexane drawn in a chair. What I want to do is draw the ring flip of that. Here's our original six-membered ring with three groups. We have a methyl, an OH, and an isopropyl. Notice for ring flips, we use the equilibrium arrows here. This is not resonance. This is a reversible interconversion between two different conformations of this one molecule, and it is an equilibrium that may lie preferentially on one side. So we use that double reversible arrow. To draw a ring flip, you usually just draw another chair. It's not always the case, but we often slant it in the other direction. I'm partial to doing it like that. So there's a chair just slanted in the other direction. Just sort of gives people looking at it a heads up, hey, I'm about to draw a ring flip. And I'll do a little bit of what I did a moment ago. I'll pick a carbon, starting with that one, the isopropyl on it, and pick a spot for it to exist over here where I know the equatorial position is going to become axial. So this was a down equatorial isopropyl group, and it's now a down axial isopropyl group. Notice down stays down, and therefore up will stay up, but axial becomes equatorial, and equatorial becomes axial. Let's work our way around the ring. I'm going to go clockwise and keep going in this direction too. So then I have an up equatorial hydroxyl on the opposite side of the ring. That's going to give me an up axial hydroxyl on that position. And lastly, there's one more. There's this up axial methyl right next to the OH. So that's going to turn into an up equatorial methyl on that carbon back there. And those are the two chair conformations that are possible for that molecule. Lastly, which one is better? Well, in the previous lesson, we said equatorial is more stable than axial. That's still true. If you have multiple groups, chances are the one with the most equatorial substituents will be the preferred one. So that was actually the one that was drawn originally. Say more stable. Because more equatorial. Sometimes it depends on what the group is. If it's a particularly large group that occupies a lot of space, we say that that's a sterically large group. Steric refers to the spatial arrangement of a molecule. For example, isopropyl is kind of large, and tert-butyl is even larger. So if you ever have a tert-butyl group on a ring, chances are it's going to force itself into an equatorial position, and everything else just has to be wherever it is so that the T-butyl gets to be equatorial. We'll see that in some examples later on. Okay, so that's what a ring flip is. There's a little animation or a little cartoon over here that sort of shows how you could imagine drawing one from a model kit in front of you. Here's just a model of a chair with one equatorial substituent. And if I imagine picturing what you could call the headrest and the footrest, there's actually multiple ways you could look at this and get that. You flip the footrest up to become the headrest, you flip the headrest down to become the footrest, and I get another chair, but that equatorial group is now axial, and that's what's always going to be true every time you do a ring flip. So let's practice this with a bunch of examples down below, starting with these flat hexagonal representations. Let's draw the two different chair conformers that are possible. Start with just a skeletal chair. This one has two methyls, one toward us with a bold line, one away from us with a dashed line. So I'm going to draw one arbitrary spot to pick where that methyl is right there. I'll say it's that carbon right there. Up at that position would be axial. Working my way around the ring clockwise, I get to this carbon right here. That has a dashed line, so that's away from me, that's down. Down at this carbon is equatorial. And then let's draw a ring flip of this, draw a pair of equilibrium arrows, draw a new chair slanted in the other direction. I'll do the same thing, I'll highlight this carbon, I'll say that it turns into this carbon over here. My up axial methyl is now up and equatorial. And then work my way around two carbons, I get to this position where I did have a down equatorial methyl, it's now down and axial. So those are the two chair conformers. Lastly, which one is preferred? Well, we have one axial and one equatorial of the same kind of group. They are equally contributing. They are equally stable. So I'll just say equally stable. One does not win in this case because there's one of each and they're the same size. Not true for B. B, I will have a tert-butyl group and a methyl, and we're going to see that one chair predominates over the other. I'll start with the same thing. I'll draw a blank chair, three sets of parallel lines. I'll pick one spot to be this carbon. I'll make it that one right there. That currently has a bold methyl, so I'm going to make that up. And up at this position will be axial. So I have an axial methyl. I'm going to work my way around the ring counterclockwise. I get to that position. That tert-butyl is also bold, and bold is up, and up at that position is axial. So there I have two axial groups. So I'm about to draw the ring flip of this, and I already know it's going to be more stable because everything's going to end up becoming equatorial. Draw your chair slanted in the other direction. That carbon right there, I'm going to say becomes that carbon. And then my up axial methyl is now up and equatorial, which means that that carbon becomes that carbon. My up axial T-butyl is now up and equatorial. Just make some more space. So which one of these is preferred? The one where they're all equatorial. And there's a good example of a tert-butyl group. And that's the group that's pretty much the largest one we've seen so far. That's going to want to be equatorial no matter what the cost of anything else. Okay, C has three methyls on it, same thing. Draw a chair. Pick a spot to start. I'll say that carbon is that carbon. They're all bold, so they're all up, coming above the ring. And then I've got a methyl that's up and axial at that position. On alternating positions, we have three up axial methyls. Draw a ring flip. You're going to get three up and equatorial methyls, like so. Lastly, which one is preferred? Clearly, the one that's all equatorial is going to be better. Okay, so there's three examples. I want you to hit pause and try the remaining 5, and then check and see how you did. Okay, let's see how you did. So D gives it to us in words, so we have to draw something off to the side, maybe to help us figure out what this will look like. It's a cyclohexane, okay, been doing that the whole time, with a methyl and an ethyl separated by carbons 1 and 3. And notice they use trans as a prefix. We've seen that for alkene geometries, We use it for rings as well, and it means the same kind of thing. If it's trans, then they are in opposite directions, and if it's in cis, they are in the same direction. So this is an ethyl and a methyl that are pointing in opposite directions. Let me redo that chair. I don't like that one very much. Let's try again. 3 pairs of parallel lines, much better. I'll pick one spot to have a methyl on it and another one to have an ethyl. So let's say that there's my methyl. And all I know is that they're trans to each other. So I arbitrarily have an up equatorial methyl. My ethyl will have to be down as opposed to up. And it's got to be on position 1 relative to 3. So if this is 3, I'm going to say that this is position 1 over here. That means my ethyl is down and axial. And then if I ring flip it, draw a pair of equilibrium arrows. Let's move that over a little bit. Draw that chair slanted in the other direction. So this carbon, I'll say, becomes this carbon. That up equatorial methyl is now up and axial. And that down axial ethyl is now down and equatorial. So here I have one of each, just like we had an A up above, but the ethyl is slightly larger than the methyl group. So I want to put the larger group in an equatorial position. That means the second chair that we drew in this example is preferred. Next up in E, we've got a methyl and a chlorine. Start with a chair. Pick a spot to start. I'll pick that carbon right there where the methyl is. It's always arbitrary where you start. You get to pick. Everything else has to be accurate relative to that in the same relative direction, up versus down. So here I have an up methyl. Up at this carbon is axial. Remember that trick of looking at the corners? It looks like an arrowhead, which points toward axial, so I know that axial is up in that position. On the opposite side of the ring, I have an up chlorine, because it's bold, and up at this carbon is equatorial. So I'll fill in an equatorial chlorine. And if I draw the ring flip, draw a chair slanted in the other way, you'll have an up equatorial methyl and an up axial chlorine. Which one's better? Well, we're competing with a methyl and a chlorine. Which one is bigger? A methyl, remember, is a C and then an H3. So it's 4 atoms clustered together as opposed to 1 chlorine atom. So methyl is larger than chlorine, which means that that second one we drew is going to be the preferred conformation of the two. F is an example of a 6-membered ring where they're not all carbons. This is a glucose molecule where you have an oxygen in the ring, but we can do the same thing. It's just going to be a bit more crowded. We have a chair where I pick some spot to arbitrarily have an oxygen in it. Relative to that oxygen going around the ring, I have an up OH, down OH, up OH, down OH, and up CH2OH going around clockwise. So to the right of that, I have an up OH, that's equatorial, a down OH, that's also equatorial, an up OH, another equatorial, a down OH, another equatorial, and then an up CH2OH, which is also equatorial. So there's one chair conformation for glucose where everything is equatorial. That makes it easy to memorize what glucose looks like. What's the other chair conformer? Well, we're going to draw slanted in the other direction. Now I'll make the oxygen down here. And as a result, every group will become axial. Up, down, down back there, and then one more back there, a little crowded. But the point is all axial. So the one where they were all equatorial, clearly preferred. G is much simpler. G just has one group, an isopropyl, and nothing else on the ring. So we're going to have a much simpler one for this. I have one chair with an isopropyl in an axial position. Actually, in the drawing, it's dashed, so I will make it down. Down on that position happens to be equatorial. If I ring flip it, I should get a down equatorial. down axial. There we go. So the first one we have is better, equatorial. Lastly, this has a tert butyl and an ethyl separated by carbons 1 and 3, and they are cis to each other, so they're pointing in the same direction. Start with a chair. Put an ethyl on one spot. Put a tert butyl appropriately distanced away, and it has to be cis. That would be cis 1, 2, 3, 1 T-butyl, 3 ethyl, and I can tell I got a pair of axial groups, so when I ring flip it, I should get a pair of equatorial groups, an ethyl and a T-butyl, and with all equatorial, you get a preferred conformer. So the point of this is for every 6-membered ring, you can draw not just one, but 2 possible chair conformations, and most of the time, we'll see one of them is more stable than the other. Large, bulky groups, what we call sterically crowding groups, like a tert butyl, will usually force the ring such that it occupies an equatorial position, making other groups occupy whatever they end up being relative to that tert butyl group, and this lets us control the way certain types of reactions work. Okay, thanks for watching.